Just let me know when you're ready. It's fine.
I think I'm ready. Do you see the slides?
Yeah, it's not full screen.
Is it big enough?
Yeah, that'll work. You can't make it full screen?
Yeah, I am trying to do it. It's very slow. I have this very old laptop, and it's taking some time. Is it good now?
Sure. Yeah, that'll work. It's not full screen now, but that'll definitely work. Oh, there we go.
Good.
Okay, great. So for the second talk today, we have Antoine from Caltech to talk to us about the Gromov-Hausdorff stability result for the positive mass state.
Thank you for giving me this opportunity to talk. I want to describe a joint work with Antoine from Stony Brook. Okay, let's start. So the precise conjecture that I want to talk about is due to Huisken-Ilmanen. I think it's one of the first stability conjectures for the positive mass theorem, and it tells the following. If you have a sequence of asymptotically flat Riemann-manifold with non-negative stereo curvature, and if the mass is converting to zero, then what you expect is that there is a subset Zi in Mi such that the boundary of Zi is very small. It's going to converge to zero, but the complement of the Zi is going to converge to the flat Euclidean free space in, say, the Gromov-Hausdorff topology. Is there any question on that statement? Maybe I can say something about how it compares to the Lee-Swan-Manius conjecture. So the conjecture of Dan and Christina, it's formulated in terms of the intrinsic flat topology, so it takes into account both the metric and the measure. Here, it's a more maybe metric version of the stability conjecture. So we don't need any assumption, but we need to remove a large piece. While in the conjecture of Dan and Christina, you might need to assume some conditions, for example, more closed linear surfaces, and then you conclude something stronger. All right. Let me mention that because of the Penrose inequality and the paper of Huisken and Ilmanen, there's a more quantitative version of the above conjecture that's due to Ilmanen. At least this is what Gray told Songhang, who told me. And what it says is that the subset Zi could be chosen so that the area of the boundary is bounded by this constant times the mass squared. And it makes sense because, again, of the Penrose inequality. So the statement of the theorem is that the conjecture is indeed true. And moreover, we can say something about the area of the region that we need to remove. So here, the statement says that if the mass is converging to zero, we might need to remove a big region, but this region has very small boundary area. And this area is almost bounded quadratically by the mass in the sense that if you take any positive continuous function converging to zero, then for all large I, the area of the boundary of Zi is going to be bounded from above by the mass square divided by this continuous function. So you cannot exactly get quadratic, but you can get arbitrarily close to quadratic. Any question on the statement?
Oh yeah, just to clarify, when you talk about Mi minus Zi comma G, so that uses lengths of paths that have to avoid Z when we talk about Gromov-Hausdorff, or?
Okay, so very good question. we chose to interpret it in, I think, the more difficult version, which is you take the intrinsic Riemannian metric. You don't want some kind of induced extrinsic metric. You want to look at the complement of Z, and that's a manifold with boundary. And you want to look at the Riemannian metric on that manifold with boundary and the associated Gromov-Hausdorff topology. So you only consider path inside the complement of Zi. Let's see. So if there's no other questions on the statement, let me right away move to the proof. Well, before the proof, of course, I should mention some related contributions, more on the side of the intrinsic flat version of the stability conjecture. There are works by Huang Li, Sormani, Huang Li, Perales, especially in the graphical case. Also that paper of Delnin and Perales. And there are some works in the hyperbolic case. Let's see. And also the paper of Allen, Bryden, and Cazares in the case, sorry, Cazares, I wanted to talk about the Cazares-Curie-Lee paper, which is, well, they studied a case where they have a Ricci curvature bound. Okay. The starting point, let me assume that M has only one end, and there's, say, no closed minimal surfaces. Let's start with the beautiful formula of a Bray, Cazares, Curie, and Stern. It gives you a lower bound on the mass in terms of some integral that you can see on this slide. And this is true for any function u from M to R, which is harmonic and asymptotic to one of those asymptotically flat coordinate functions. So that's really the starting point. And note that we only need a weaker version of the full theorem because we can ignore the scalar curvature term here. And then what we do is we look at three functions, U1, U2, U3, which are those kind of functions, so harmonic and asymptotic to one of those coordinate functions. And you want U1, U2, U3 to be asymptotically orthogonal coordinates, right? Now you can think of this U as a map from M to R3. And you want to look at the subset of M, where this map is very close to being a Riemannian isometry. Looking at this set was first appears in a preprint of Cong Dong. All right, let me move on. So what we do concretely is, in order to measure how close you are to an isometry, is the following. You look at the following function f, which is defined using the U1, U2, U3, okay? And this function exactly measures how close your differential is to a linear isometry. Now you're going to look at a sublevel set, so f minus 1 of 0 epsilon for an epsilon very small. You can imagine that this omega is a neighborhood of infinity where f is really close to being a Riemannian isometry, at least locally, right? And heuristically, at least, you want to say that this region is very big, and you would prove the statement of the theorem. There are two main steps in order to do so. So the first step is to show that one of the level sets of F has very small area, meaning that compared to M, if M converges to 0, the level set will have area convergent to 0. And you can think of this level set as being the boundary of a region like omega. So this now you have a region which is a neighborhood of infinity it has a very small area boundary. And you know that locally it's almost isometric to a flat Euclidean free space. So the second step is to show that this really implies that this region is close to the flat R3 in Gromov-Hausdorff. So not exactly that. You in fact need to remove some small volume subsets. But modulo that, you get the region that you want to.
Okay, can I ask a quick question?
Yes, sure.
When you say the Gromov-Hausdorff topology, the distance that you're putting on this F inverse from 0 T naught, is that the restricted distance from the hole or an intrinsic path distance?
Right. So as I said to the metric, here you want to look at the Riemannian metric of the subset. So you're not inducing or restricting any extrinsic metric from M, for example. You just look at this neighborhood of infinity. So this subspace of M. You look at this as a Riemannian manifold with boundary, and then you look at its own Riemannian metric.
Okay, thank you.
Any other questions? Let's see. Okay. So I'm going to be okay, I think. So let's start with step one. Step one, again, is to find one level set, which is very small. And I remind you the starting point, which is BKKS. So you're assuming that the mass is very small. So for each of the UI, this integral of basically the Hessian square is going to be very small. And on the region where you know, this region omega, where U is close to being locally a Riemannian isometry, the gradient of U, you can think of it as basically being of norm 1. So if you think about that for like 1 second, if you have a control on the mass, then you have this control on the Hessian of U, so you have a control on the L2 norm of the gradient of F, just because F is defined in terms of the gradient of U, right? So what I'm saying here is that BKKS directly implies that you have an L2 norm of the gradient of in terms of M, the mass. Okay, what we want to do is to find a small area level set of that. What we are actually doing is to try to find a small volume region between two level sets. That's easier. And then you just apply the co-error formula that will give you a small area actual level set. Okay, so now what we really want to do is to find two level sets such that in between the volume is very small. And again, I'm talking about level sets of F. The main idea somehow is to prove a version of the capacity volume inequality, which is originally due to Poincaré, Weber, and Szego. And I'd like to point out that there's a very nice note on this by Jeffrey Doré-Gui. I think that without this note, I would have not known about this inequality. So what is this inequality? This inequality relates for, say, any bounded open subset of R3, the L2 norm of the gradient of a function on the complement. So you want this function to be equal to 1 on the boundary of this subset A and 0 at infinity. So you want to compare the L2 norm of the gradient of such a function to the volume of omega. Sorry, to the volume of A. There's a typo here. And roughly speaking, you can show that the volume of A is bounded from above by a constant times a power of the L2 norm of the gradient of any such function. And here the constant C3 is optimal. And you can guess that equality is going to be achieved if and only if A is above. So it's not the first time, of course, that capacity appears in mathematical GRs. So there's the work of Bray, who used it very early on. And then there's the work of Bray Miao, of Jeffrey Joragui, of Miao Pengzi, and also Joragui Perales Portuguese, which is more recent. But somehow the use is pretty different from what we're going to do here, which is, by the way, is very simple. Basically, here's the thing. So remember that F is measuring how close the map U is to a Riemann isometry, right? And on omega 0 epsilon, so omega 0 epsilon again is the region where F is between 0 and epsilon. So this F is going to be, sorry. So here I want to use U. I'm sorry, this is a typo. Oh gosh, many typos. Anyway, so you can think of this omega 0 epsilon as covering a region of R3, right? Because the map U is almost an isometry. And a priori, one difficulty is that even if locally you are diffeomorphic, it's kind of hard to control the multiplicity of such a thing. But there is a useful version of the capacity volume inequality, and here it is. So what you show is basically that there's a S0, such that the volume between, so the level set S0 and the level set S0 plus epsilon over, say, 1,000 is going to be well controlled by the mass. And I want to quickly explain why this is just the capacity volume inequality. Let me go back to the capacity volume inequality. You're bounding, of course, a volume by the L2 norm of the gradient of a function. So here the function is going to be f, the big F. And that's why you just need essentially to follow the proof of the original inequality. And you just need to be careful when choosing the S0. It's not going to work if you choose any F0, but you can choose S0 so that the level set at S0 almost has, has area comparable to the smallest area of the level sets for S between 0 and epsilon. Is there any question on this lemma?
Yeah, I have a question. Is this use of the capacity volume inequality the main point that differs from Dong's original paper in getting rid of the uniform asymptotics? Is that what this is for?
I think so. At least this is how I understand it. So in Dong's paper, he really needs at least a few things, and at least the fact that you're uniformly asymptotically flat. Integration by part argument. But using this inequality, you don't need any uniform control on how fast you're converging to the Euclidean metric. So you're right. I think you're right that this is the main point. But there's a second main point which appears in step 2, in fact, because if you look at the preprint of Song Han, he's not really able to conclude something about the Gromov-Hausdorff topology.
Right. But I was just saying, yeah, so of course, yeah, there's the extra bit about Gromov-Hausdorff, but I mean, in terms of the role of this lemma or this use of is mainly about the uniformity assumption, I'm guessing. And then later, the second part you're talking about is that.
Exactly, yeah. Exactly.
Okay, all right, thanks.
Okay, so let me summarize what we did so far. Right, so we have this L2 norm bound on the gradient of F in terms of the mass, and then applying the capacity volume inequality, you conclude, partial conclusion, that the volume of the region between two level sets is very well controlled. So this volume, of course, you want it to be thick enough. So it's I mean, this region, you want it to be between S0 and the S0 plus a uniform quantity, which is this epsilon over 1,000. So once the lemma is proved, step one is done by applying the Carré formula and Cauchy-Schwarz. So quickly, what I mean by that is that you have the integral of the area of all the level sets between S0 and S0 plus epsilon over 1,000, right? You can write it using so the Carré formula, you can write it as an integral of the norm of the gradient of f. So this norm of the gradient, you use Cauchy-Schwarz, so you get the norm of the gradient of f squared, and another term, which is the volume. So you control both by what we did before. So that's why you get this mass square over epsilon fluid. And right, so from that you conclude that you have a level set that has very small area, if the mass is very small. So you see that here, at least the rate, I mean the scaling is the correct one. So you're really looking at a level set that's whose area is bounded by m squared. So this is the right power. However, there's this epsilon lurking around, and in the second step, this is going to cause some problem. But this is basically the end of step one. And we move on already to step two. So step two, the intuition is that now you have this T0 such that the region where f is between 0 and T0 is this big neighborhood of infinity, and on which the metric is kind of flat, close to flat. And moreover, you know that the boundary of this region is very small. So at least on the heuristic level, clearly this neighborhood should be close to R3 on a heuristic level. Right. So the question is, why is step two even non-trivial? So let me give you a little example. If you consider this long, thin, solid cylinder C1, which is a little ball in R2, a little disk in R2 times a very long interval, 0 to 100. You can imagine that this is a solid, thin cylinder inside R3, and you want to think of delta as being very small, okay? Then, if you remove this solid cylinder from R3, the complement with respect to its own Riemannian metric is very close in Gromov-Hausdorff to the flat R3. And moreover, the boundary area of the thing that you removed is also very small. So that's pretty clear. But now let's consider an even thinner cylinder that you can think of as contained in C1. So C2 is what? C2 is an even smaller disk times 0, 100. And now you're looking at R3 minus the bigger cylinder plus the smaller cylinder. So what you have done is, in fact, you carved out from R3 a kind of solid tube, right? And as it's a fact that when delta is very small, this thing has very small area boundary, but it's always very far away from the flat R3 in Gromov-Hausdorff. Do we have a question on this fact?
What metric are you putting on it?
Right. So again, every time I'm talking about Gromov-Hausdorff, I want to think of the Riemannian metric on this subset as a Riemannian manifold, right? So you
But
know,
it's disconnected.
Did I make it wrong? So let's see. So you're looking at R3 minus a big cylinder, but then you add the thinner cylinder, and you have this connected set, right?
It seems disconnected to me, but
They're finite cylinders, Christina, right? So they have a top and a bottom. You just go
they're
down to-
finite
yeah.
cylinders.
Yeah,
Okay, the
right.
cylinders. Yes, of course, of
Yeah,
course.
yeah.
Sorry. Yes, my apologies. Mhm.
So it's a solid finite height.
Right.
And so here you really do have a connected set. Yeah. So is anyone okay with that example? Basically, what this example means is that maybe you have a small area boundary, but you're going to be very far from either 0 or R3, right? In the Gromov-Hausdorff of the point, just because you have those kind of inner tubes that mess up with the distances. Right. Another way to say that is imagine that you have this R3 minus the thick cylinder plus the thinner cylinder. And if you take a point in the middle of the thinner cylinder, then in order to get from this point to basically outside, you need to first go through the thinner cylinder to get back to the region where the gluing was happening. Okay, I think that's more confusing if I try to explain it, so I'm going to leave it to you. Now, of course, you can imagine much more complicated situations. This is really a simple case, but it illustrates how you want to approach the problem and what could go wrong. Essentially, in order to prevent those kind of situations, you're going to want to remove cylinders of the type C2. Okay. Right, so I said also that there's the second issue that we really want to use the intrinsic Riemannian metric. So that's basically the questions, many of the questions that you asked were about this. How do you measure the GH distance? You really want to use the intrinsic Riemannian metric and not the restriction of some Riemannian metric from ambient space. Okay. Now the main idea is really to cut the space R3 into very small 3 cubes and look at the pre-images Ci of those cubes in omega 0 T0. Remember, omega 0 T0 is this neighborhood of infinity that you want to show is very close to R3. Right, and I think F here should be U. I'm very sorry about this confusion. Then in each cube, what you do is you're going to remove all the small connected components. So now you have just one connected component, and what you can show is because the boundary has very small area, this one connected component left is very big in terms of volume. If you think of what this is compared to the previous example using those 2 cylinders, what you did is really to remove C2, the thinner cylinder that was causing problems. So now you get in each Ci a smaller region Di. It's just—
Sorry, what do you mean by remove small connected components? Small connected components of what?
Of, again, Ci. So what is Ci? It's the pre-image of, say, a cube in R3. So it's a very small cube, you have to imagine. And you look at its pre-image in M, the asymptotically flat manifold, and you will have sorry, not in M, in omega 0 T0. So omega 0 T0, remember, it has almost full volume and it has very small boundary area. So if you look at just in C1, say, you will have several different components in general. Let me maybe go back to this. So say, again, imagine that C1 and C2 are very high, okay, 0, 100, and you're looking at around height 50. You're looking at a very small cube centered on this axis, z-axis. What are you seeing when you intersect with R3 minus C1 plus C2? Well, what you're seeing is the big part R3 minus C1, and a disconnected component, which is coming from C2 in this cube. And what you do in that particular cube, well, you just remove the intersection of that particular cube with C2. So you're left with one connected component, which has still...
You remove whichever one is smaller?
Right, so you can prove that in such a situation, since the boundary area is very small, there's only basically one component which is going to be very big, and all the other components are going to be very small. That's basically the isoperimetric inequality in the cube.
So the cubes are small, but they are not small compared to M. M is much smaller.
What is M here?
The mass, the delta.
Well, yes, exactly. So M is even smaller, very smaller.
Thanks.
So the cubes are going to be small, but you think of them as of fixed size compared to the mass, which is going to 0. And so the goal is to say that when the mass is converging to 0, your sequence is, after removing stuff, arbitrarily close to R3. But the arbitrarily close is depending on this epsilon and depending on the size of the cube. All right. Right, so to put it simply, what we did is we changed a little bit the region by removing inner cylinders of the type C2 that appeared previously. And because of the area, we can prove that if you put together those little di together back, and you maybe have to enlarge it a little bit, what you get is going to be a very big volume region, almost full volume region with very small boundary area again. And this time you are from a Hausdorff close to R3. So I don't know how much details you want to know about these two steps, but let me know if you have any more questions, because I'm really going too fast, I think. I'm not going to be able to last an hour. Maybe 2 comments. One is, all right, so in the first step, you did find a level set of area at most m squared times a constant. This constant depends on epsilon. And so in step 2, you really need to take this epsilon to go to 0. So that's why at the end of the day, you cannot really conclude or the conjecture of immanent. Remember the fact that the boundary area can be chosen to be smaller than c times m squared. So let me talk a little bit about the interaction with the intrinsic flat stability conjecture. We can try to wonder what happens if now we suppose that there's no closed minimal surfaces. For example, is it possible to show that the regions that we are removing here do not count much for the intrinsic flat topology? So how to, for example, let's imagine we want to maybe use this proof and use the assumption that you don't have closed minimal surfaces. How do you show that the thing that you remove is going to not count for much? Somehow this condition on having no closed minimal surfaces is hard to use. It's because it's somehow local condition. It's global, but minimal surfaces are very local. I'm going to finish already with some related things I wanted to talk about. So there's this general motivation question, which for me is fascinating, which is, say, in general, what can you say about intrinsic flat limits? And I've been thinking a lot about that question in the particular case where the intrinsic flat limit comes from a sequence of cycles, minimizing the area. Let me mention some intrinsic flat stability results. For PMT, we already saw several results. There's a kind of general stability result for the intrinsic flat topology to Allen, Perales, and Sormani. And also more recently, there's a result of Allen, Bryden, Cazares for the Laruelle theorem. If you think that your name should be here and you don't see it, feel free to yell at me. I really want to know what's going on. It's just very hard to keep up with what's happening. So just let me know. What I want to kind of promote is another recent stability result in the context of intrinsic flat stability, intrinsic flat topology, which is related to the volume entropy. So recall that the volume entropy of a closed manifold is nothing else than the exponential growth rate of the volume of balls in the universal cover. So it's a measure of the complexity of your measure. And there's an important inequality called the volume entropy inequality, which is due to Lesson, Courtois, and Galop. And it says that if you have a closed hyperbolic manifold, say I mentioned at least 3, and you put any other metric on M with same volume as the hyperbolic metric, then in fact the volume entropy of G is at least the volume entropy of G0. And moreover, equality happens if and only if G is isometric to G0. And I wanted to mention that because there's a corresponding stability result, which is the following. So if now you have a sequence of metrics, any sequence of metrics on M with same volume as G0, the hyperbolic metric, and if the volume entropy is converging to the entropy of G0, then what you can say is that MGI converges to MG0 in the intrinsic flat topology. One thing that I find maybe noteworthy is that here you don't need to add any additional conditions compared to the original statement of the theorem. For example, you don't need a diameter bound. And also the strategy of proof is really the direct one. So maybe in the spirit of, I don't know, Longley Sormani, where you want to use, say, the Wenger compactness theorem, and then you show that the limit is exactly what you expect. So this strategy somehow is very natural, but it's pretty rare that it actually works in some kind of generality. But here it works. And also one thing I wanted to mention is that something that makes the problem more tractable here is that you can embed such an M in a natural way in some kind of big ambient space where it can compare things. I'm not only mentioning this result for self-promotion, there's also a kind of link with scalar curvature. In fact, Perelman showed that if you are a hyperbolic manifold of dimension 3, and if you put any other metric with scalar curvature lower bounded by -6, then the new volume is going to be at least the hyperbolic volume. So this is a famous result of Perelman. So if you add this result of Perelman plus the above stability result, plus a conjecture of Egel-Stern-Thurston relating the entropy to scalar curvature, in fact, you should conjecture the following. So if M is a closed three manifold which is hyperbolic, And if you put any sequence of metrics with scalar curvature lower bounded by -6, if you assume that the volume converges to the minimum, which is the hyperbolic volume, then the sequence should converge to the hyperbolic metric in the intrinsic flat topology. And again, you have no additional assumptions here. This is somehow everything that I prepared. So I'm sorry that I was a little bit fast, maybe. Thank you for your attention.
Thank you very much. If I can ask more questions about this last slide, actually, what's the theorem of Perelman and the conjecture of Egel-Stern-Thurston?
Right. So I'm going to say it in words. What Perelman showed is that, say you start with mg0. So mg0 is this closed hyperbolic Thur manifold. And now let's put another metric, which is which you suppose has scalar curvature at least -6. Okay. Then Perelman showed that the volume of this new metric is at least the volume of the hyperbolic metric. And you have equality if and only if the new metric is isometric to the hyperbolic metric. So now the corresponding stability statement would be, okay, you have a sequence of such metrics with volume converging to the minimum volume, right?
Right. Huh.
And even though it's not positive scalar curvature, I think negative scalar curvature is also very interesting. And oh, yes, so the conjecture of Egel, Sturm, and Thurston.
Yeah.
It's telling you that if you have a scalar curvature lower bound, say scalar curvature larger than -6, then you have an upper bound on the entropy. And so that means that if you put all these elements together, if the conjecture of Egel, Sturm, Thurston is correct, you just combine it with, well, what I showed with the entropy, you should get the statement of the conjecture.
Oh.
But of course, people are still pretty far from, I think, pretty far from this conjecture.
Right.
And the
sorry. So when you say suggest, you actually mean it actually implies, right? Is that what you're saying?
it implies, yes. It's just that the conjecture is still wide open.
Right, of course.
And also, well, Perelman, of course, he uses Ricci flow. I don't know how much you can show using Ricci flow. I mean, we discussed about that an hour ago.
I mean, do you think that the... Sorry, you finish what you're saying?
Yeah, so what happens, of course, is that if you start with the Ricci flow is going to deform the metric to the hyperbolic metric. And so what you can hope maybe is to use the flow somehow to construct a converging sequence, but it seems hard.